welcome in. So this particular video is going to try to explain to you in a much more generalized way why the volume of a pyramid is 1/3 of the volume of its prism. Now you can see here the prism, which is the one in the top left corner. So I am choosing a rectangular base, and then the pyramid is just below it there. Now the apex, the top of the pyramid, doesn't necessarily have to be right in the middle. Okay, it can be anywhere, okay, within. So it will work regardless, okay, of where that apex actually is, as long as it's projected, okay, up above there. Now, my goal in this video is not going to be just to show you where the base is rectangular. It will be, and that's the reason why this video is much longer than most, it will be a generalization to try to show you the steps without using calculus and just have intuition and understanding of just algebra. Why do we have this 1/3? Now, that's going to be the call, right? The ultimate goal. So this is the question. Now we going to assume, well, we're not sure exactly what it is. Now I will assume that it's some constant, but I just don't know what this constant actually is. So I know that it's the base times the height, but what portion of that prism it is, I don't know that it's 1/3. I mean, we know that because we see these formulas all over the place, but you might wonder why. I've done a very short and intuitive example where the prism is actually projected out to be a cube. And, I can put a link up above there. It has satisfied a lot of people, but it hasn't satisfied everybody. And it also has tinkered in my mind that I should probably put up this video to let people know what the general concept would be. So step one, let's actually show that this C for the base being rectangular is actually 1/3, right? So that's the first thing that I want to be able to show. Now this is general. The width itself, so you can assume that this is the width, this is the depth, and then this is the height. So I'm not going to kind of put them in here. I'm going to remove, okay, these volumes for the time being because I need space in here. So what I'm going to start with is I'm going to duplicate this prism. I'm going to make two of them. So I'm going to take this one and I'm going to duplicate it. So here is another one that I have in here. And I'm going to stack them on top of each other. So that means I have twice the volume of the original. Okay, so that's what I'm going to try to do. Here they are stacked on top of each other. So that's what we have presently. So that means this is going to be height h, this is going to be height h. The actual width does not change, and the depth does not change either. But I have twice the volume, right? So it should not shock you in any way that this is really twice the original volume, which is going to be width times depth times height, because I have two of them. Now, what I'm going to do is I'm going to insert this pyramid inside. And so one, okay, will go at the bottom. So I'm going to duplicate because I'll need this one as well. So I can take this and I'm going to just stack it in here, right? So that's just part of one. That's that first pyramid. The other one is going to be a mirror reflection. So the base is not at the bottom, but the base is on top. So it's a mirror reflection. So it's almost like I'm flipping it. Now, we can't really flip it unless it's, of course, the apex is at the centroid, okay, right there. But that doesn't have to necessarily be the case. So let me just flip this and put it back in. Just a moment. All right, so now what we have is we have two of our pyramids. So they're basically just mirror reflections on top of each other. And so within here, what I have is I have the two stacked prisms on top of each other. Now, next, what I have is I have two of those pyramids. Now, so I have two of them. So the volume itself, so this is going to be width times depth times height. Now, it's supposed to be 1/3, but we don't know that. So I'm going to just put C. I don't know what this C is. I want to show that it's 1/3, okay, of the whole thing. Now, I hope that you can appreciate, okay, and this is going to take a little bit of visualization from you. So you have one pyramid, you have the mirror pyramid on top. And now you have actually four other pyramids here, right? So you have a pyramid, so you have two on the side right there. So you have two pyramids on the side. So what I mean by these, okay, is these are pyramids. I'm going to duplicate this because I just want to show you one by one. So you have these two pyramids. I'm going to just, get rid of this, all right, and then get rid of this so that you can see this, okay, and then I'm going to get rid of this right here. And as you can see here now, I have two pyramids, right? So I have one on the right and then one on the left. Now, these two particular pyramids, okay, the way that I have written it out, so they have, okay, so within here, they've also now their base is different. One is on the left, one is on the right. Okay, so I'm going to just write out, okay, so within here, and I'm going to designate, so from right here, from this, okay, so it's going to have a certain height, okay, right there, okay, and then this one is also going to have a certain height. They don't have to be the same height, by the way. All right, so I'm going to call this one, let's say, height 1, and I'm going to call this height 2. All right, so height 1 and height 2. And this left pyramid, so this one right here, is going to have a volume equivalent equal to, so C, because I don't know, okay, if we really have a third of the full out prism. Now, its base that I have is going to be actually the depth multiplied by 2, so multiplied by 2h, and that is this right here. So this right here, right, and this right here. So that is its base right there. And then multiplied by its height, h1, that is the volume of that. Again, we still don't know what the C is. Now, this right here is going to have also a volume of C, okay, depth times 2h, but this is going to be h2 because it might have a different height. I'm not saying that this is all symmetrical. It might not be, so I'm going to call that h2. The one thing that I do know, h1 plus h2 is indeed equal to w. So that is something that we should keep in mind. This is h1 plus h2. And that is that pyramid. Now, I also will have the same thing, right, with the front and the back. So I'm going to have the front and the back, and that is going to now constitute my pyramid, the bottom one, the top one, two on the side, and now one in the front and one in the back. So let me duplicate this right there. Bring it down. I'm going to actually bring it down over here, just below it. And this is what I am referring to now. Hope I'm not going to erase the wrong things here. So I have to erase that. All right, I have to erase this. Okay. And those are my pyramids right there. So that is the front one and then the back one, okay, that I have in there. So, and I guess I can erase this. Those are the front and the back. And now I will have its volume. So I have now the front one. So the one in the front, so that's this one right here. Notice that this has its base. So the volume, again, this is going to be some C. And then it's going to be, now this is going to be width times, so its base is, so this is 2h. It's the front and then the 2h, because that's the size of the height, multiplied by, now its height, right? So as we have the height, let me move this out of the way. So its height, okay, so it's going to go, right? So it's going to have a height in this way. Now it's very difficult to draw because it's from the base to the front to that apex where it's connecting to the other one. So I'm going to call this H3, right? So that's from here to here. And now that is going to be H3. That's the volume of the front. The volume of the back one is going to be, so again, we still don't know if pyramids are really a third of the prism. So that's C. Now the back, again, it's still W times 2H, but its height, okay, is going to be this height right here from the back to the apex, and that is going to be H4. So that's what I have now. So I have deconstructed my prism into really 6 pyramids. Now that volume, so this volume, which is of the entire prism, so I'm going to just take it and bring it down here. That's the volume of the original prism, right? This is equal to the 2 original, so this is this one and this one right there. Okay, so that is going to be, now I have 2 of them, so this is going to take now that volume, okay, so we have right there, okay, now I have 2 of these, so I'm gonna just copy it, bring it down, so let's paste it right there. I have 2 of those, plus I have 4 of these pyramids, 2 on the side, 1 in the front, 1 in the back. And so for those, okay, so what I have is, so I'm going to take that, I'm going to duplicate it, bring it down in here. So that's 1 of them right there. Now plus, okay, the other ones. So let me bring all of these down. There you have it. All right. So now what I want to be able to do is I want to be able to solve for this C. So what is this C? Now notice it's common to all the pyramids, obviously. And then on the left hand side I have WDH and then I have the 2. Now the first thing, okay, so what I will do is I'm going to just do the algebra in here. So the 2, I'm going to try to make this small. I'm going to keep the C in there, so WDH. Now, plus, now notice that these are sharing the D, the H's, the 2's, and the C's. So I'm going to take that out in there. So this is going to be 2, okay, that I have. 2C, then the D comes out, and the H. And then, so I'm going to leave off, so this is going to be the H1 plus the H2. That are these 2 terms that I have. Now, plus, now I'm going to take these 2 terms, and notice again I have 2C. Now it's going to be W, H, and then what I have in there is H3 plus the H4. That's what I have there. Now, I want you to notice that h1 plus h2, so this is, I pointed it out over here, so h1 plus h2, that's the entire height, that's just w. So that whole thing is just w. So if I rewrite this whole thing, I'm going to duplicate it, bring it down, then what you're going to notice is, well, this is just w right there. And now this right here, what I have, h3 and h4, so notice this is right there. Well, what is that? That is just d. So if that is just d, then what this becomes is 2CWHD. And all of this is equal to 2, and that was WDH. So if you do this all together, right, what do you now notice? I can take out the 2. Notice all of them have W, W, W. All of them have a D. All of them have an H. And it's only C that remains, right? So how many? I have C plus C plus C, because that's the only thing that remains in there. Now, I hope that you can see from here that now this 2 and the 2's will cancel. So W's cancels, D's cancel, H's cancel. So you have 1 is equal to 3C. Well, C is 1 over 3. So that's algebraically showing you that for any pyramid which has a rectangular base and the apex is fixed somewhere on the top there, you can construct this. You don't need calculus, but you do need a little bit of visualization and intuition. And you can come up and indeed show that it is 1 over 3 that you have, okay, as your constant that must be in front. So if there's a constant, it has to be that 1/3. So that shows you that a pyramid, okay, with the rectangular base will be 1/3. Now from here you might say, well, that's all great, and that's some of the comments that I've got on the video which I just provided, intuition with the cube. Said, well, but what about other bases, right? And you are correct. So you do not have to have a rectangular base. What about a triangular base? What about if it's a pentagon? What about an octagon or some other polygon in terms of its base? How would you do that? Would you want to be able to show all of this on a continuous path? So that's step number 2. Our next step now is to be able to show that with a triangular base, and I'll do a specific triangle base, and show that it also means that it's 1/3. And then from there, the extrapolation to all others is going to now be so much easier, so that I can hopefully convince you. So I'll be right back. I'm going to just draw out the triangular that we will consider to prove. So here is the triangular pyramid that we're going to try to work with. So that's the pyramid itself. Okay, so it comes from this particular prism. Now I am going to do a special pyramid where the apex right here is basically this point, this vertex right here at the top. Now once I have that, I'm going to be able to generalize it to any, so that means it can be anywhere, okay, in terms of the apex itself, but I just want to focus on this one first. The reason is because I want this to be broken down, and as you can see here, it's going to create 90 degrees within here, and that's going to be crucial to be able to show all other prisms and then pyramids, that it is indeed 1/3. That's that constant in front of the volume equation that we have. So I'm going to approach this in the same style. So the first thing that I'm going to do is I'm just going to let you know. So the triangle I'm interested in, so this is the base itself right there. That's the base that I have. So that's the same base that I have right here. Let me just remove that. And this particular, is going to be the depth of this triangle. So it's kind of like the height of the triangle, but I'm going to use the height right here. So that's the height itself. So this is the height right there that I have in there. So it's the same thing as here. So that means this is the height of the pyramid. That's my height. This is going to be considered my depth right here. So that's the depth of the pyramid itself, or the prism. And then this right here is going to be the width that I have, which is the width right here. And I'm going to just kind of remove this for the moment. And that's what I'm going to use. I'm going to use this as my width, and this is going to be my depth in here. Now, what that tells me is, notice that the area of the triangle is going to be width times W there. We typically say base times height, but I'm 3 dimensions and I don't want to use height multiple times. I just want to use the height as the height of the pyramid or of the prism. So that's my area of the actual surface that I have, which is the triangle itself. Now, let me remove all of this and say that, well, the volume of this prism would have been just WDH. It's the same thing that I would have in here, except, I would have a half because I'm dealing with a triangle. So that's the volume. Now, I'm going to, stack these again. So I'm going to duplicate and stack them on top of each other. So there's 2 of them right there. All right? So that's what I have. Now, this will create the same thing as I did with the rectangular one. It's going to create another pyramid on top. The only thing is, this looks like an optical illusion. So the unfortunate part is it looks like this one looks smaller than this one. It is not. Notice that if I stack them like in this, right, you can see that the height's the same and then the base is the same as well, right? So it looks like an optical illusion. So I'm really just stacking one on top of the other. This is exactly what I'm doing inside of here. So I have this right there as my 2 pyramids. They are identical. And now, so what I have is what I want to be able to show in here is, so this would have been, the volume of the pyramid itself, but I have 2 of them, right? So I have 2 of these volumes, in here. That's what I have. Now, I'm after showing that the volume is 1/3 of the prism, right? Remember that. I want to show that it's 1/3. So that's kind of the key in here. Now, the trick that I'm going to use in here is going to be the same trick as I used with the rectangular one. I'm going to break down my prism now into these 2 pyramids. And then also, you're going to have an additional, and notice, so that particular, I'm going to try to use a different color. Now, it's going to be hard for you to see, but this is going to be, the base. Now, notice it's rectangular, right? So that is the rectangular base right here. And that prism is now constructed of those 2 pyramids, one stacked on top of each other, and then this an additional pyramid, except this pyramid has a rectangular base, which we know what the actual formula is for a rectangular base because we just proved it. And that would be going into, so this one right there, so it's going to be very hard for us to try to visualize, but it's like looking from the back interior. So in 3Ds, I don't know how else to do this, right? But it would have been this right there. That's kind of, looking out. And that construction right there, so that's basically like constructing another one right here on top and then adding it on. Now, I don't want to do this here because it's going to, it's going to complicate this for me. But I hope that you can visualize that there's this rectangular pyramid, okay, which goes in and its apex is the same apex as those two pyramids in here. And if you take, this right here, so 1, 2, so that's 2 of these, just called it 2V, so the volume of each, plus this rectangular one right there, which, by the way, we know what this volume is. The volume of this orange one is, because now we know that it's a third, right? So it's a third of the base. Now the base itself is the width, right? So that is the width right there times 2h, right? Because it's twice the height. So that's, height going 1, 2. So that's the 2h right there. That's my base. And its height is really the depth, right? Because it goes from the base and then it's the height, so goes to the apex. But that's the depth. That's what we've defined, right? We said that this is going to be the depth, right? Right there, that's the depth. And then from here, so this point, we can't see it because it's right at the apex. That's the depth itself. So this is D, and that's the volume. So now I do know that this right here, duplicated, plus 2 of my pyramids is going to be equal to 1/2 WDH, right? That's what I have right there. Now let's actually solve for this V, okay, within here. So that's what I want to be able to do. So now I'm going to shift, this entire term over to this side. So this I'm going to shift over. So let's rewrite this. Oh, and by the way, so because I missed this here, I just want to show you. This is no longer a half, right? Because that was the volume of just one pyramid, but we stacked them on top of each other. So this is really times 2 because we have 2 of these. So I have to be careful here. I'm going to put this times 2 like so. So now what I would have is in here, I'm going to take this, all right, right there, and I'm going to extract, okay, the 2 out of there. So this is going to be now, so this cancels with this. This is WDH, right there. And then this is going to be minus, and this is going to be a 2 over 3 W, and again notice DH right there. That's what I have within here. So that's 2V for that. So now notice WDH, W this, I have a 2/3, so this is going to be 1/3 of WDH. You're seeing this 1/3 appear there, and you might get excited in here. However, we have this 2. So if we divided this by 2, so if I get rid of this 2 and divide this by 2, so notice what's going to happen. 1/3, now I'm going to put a bracket in here. Okay, so this is 1/2 WDH is equal to V. V was the volume of that pyramid. And now notice that I put the 2 in here because what I wanted to show you is that this right here is just the area. So that's just the area of my triangle, right? Of the base times the height. And then again, you have your 1/3, which now shows you once again that the constant indeed is 1/3. So that is the breakdown algebraically for this particular pyramid. Now, from here, it is actually rather simple because this is really the key that we wanted. We wanted to be able to show that a triangular pyramid, now I took a special one because, you know, if you're really trying to pay attention, you'd say, well, you chose the apex to be right at this, right? Right here at that vertex. But the apex, you know, didn't have to be here. It could have been here, here, here. It could have been somewhere different, interior. And then in that case, this argument would have fallen apart. And you are correct. It would have fallen apart. However, now I can construct any that I like with any apex. And what I would want you to visualize, okay, so now I can take any triangle. If I have this, I'm done. Meaning, if I've shown this for this special case, I am actually finished. Because of the fact that now if you take any triangle, right, and you try to redo this. Let me just kind of redraw it, so bear with me. All right, so here it is. So if you have a regular prism and you're not taking the apex to be here, maybe it's here, maybe it's here. So let me just draw it, okay, within there. So let's say, you know, that my apex was somewhere, you know, maybe somewhere over here, which means that now I would have to draw this, okay, and I would have my pyramid would have been something like this. Would have been definitely different looking than the one that I had. And now you might say, well, it falls apart and you can't do that. Now, is it still true that you're going to have your area times the height and then there's going to be a third? Yes. Why? If we look at the top view, right, at the top view, so if we look at that triangle at its top view and we're looking straight down, then now, so that particular, you know, triangle, so this is from the top, all right, so that I have. And I'm looking straight down, and that apex, let's say that it fell somewhere over here, and I'm looking down on it. Now, look what you can construct. You can now construct, okay, from this apex, basically, these triangles, right? Now, the triangle, what I'm actually doing is, I'm creating out of this pyramid, where the apex can be anywhere, I am constructing now 3 separate pyramids. 1, 2, and 3. Now, what's special about them is that the apex, because the way that I've constructed, if we looked down on it, we are actually reconstructing 3 of these style of pyramids. That's what we're trying to do there. So this is from the top view to the bottom view. So this would have been volume 1, volume 2, volume 3, right there, where let's say volume 1 is just the pyramid on its own. Okay, if I now draw it out, that's the height, right? So it would look something like this, okay, within here. And you would have been constructing it in this way. So that's from the, and then this is right there. So that is this piece, where this right here, so this one, okay, so that's this piece right there. So that's this piece right there, right? This face, okay, so that you have there, okay, so that's this face. Okay, this right here is this, and then this right here is over there. And now again, once you have this, your apex is right here. And what you've created is, so this is 90 degrees, this one is 90 degrees, and we're back to the same argument as that. So you have now divided any, where the apex can be anywhere, and you can break it down into 3 triangles. And guess what? Each of them, so each of these we know is 1/3, okay, of the actual volume of the prism. And if you add them together, that 1/3 that you have is now, it's what it's going to be is 1/3 of that first volume prism, okay, plus 1/3 of the volume prism 2, and then 1/3 of the volume 3 prism. And of course you have a third everywhere. So there is nothing else that you need to show. And now, remember how when we were doing this and I did it with the rectangle, I said that I took a rectangle especially, okay? It was a special case. But now, what if you said, well, what if it wasn't a rectangle? What if it was, where the base was something odd, maybe it was something like this, okay? Like a trapezoid or something like that. And then, so I'm looking down at this, and then, the apex is somewhere, maybe over here. Again, I'm looking from the top down. And then the pyramid would have been shifting in this way. So look what happens, okay, as you do this. This will just break down for you. Now, this, in this case, it has a 4-sided base, whatever this might be. And you can break it down once again. So this would have been one triangular pyramid. This would have been, your second triangular pyramid. This would have been your third triangular pyramid. And this is your fourth triangular pyramid. And guess what? Each triangular pyramid has the volume when the 1/3 appears in it. And now you can just add them together. So you can say T1 plus T2 plus T3 plus T4, which is the total volume, okay, of this entire pyramid. Now, of course, looking from the top in this way, and all of them have the 1/3. So you can just take out the 1/3, add all the volumes together, and you still have that. So I hope that convinces you. Now, what you can do is you can now take any base. It doesn't have to be, rectangular. It doesn't have to be 4-sided. It doesn't have to be a triangle. Okay, you can take any one or any sides that you like, as many as you want. So, for instance, something like this. Again, this is looking at the base from the top, and then now you can put the apex anywhere in here. And now, so from the bottom going up, right? So it would have been looking like that. And what do you notice if you go to every single vertex right there? What you're creating is you're just creating, so how many? 1, 2, 3, 4, 5, 6. You're creating 6 triangular based pyramids, which we know 1/3 has in it as a constant. So now when you add them up, they all have a 1/3, and it will give you the volume of a general pyramid. So this you can now keep going, and I hope that this will now convince you that that 1/3 indeed can be used for any pyramid where the apex is somewhere, okay, above that. Now, another thing that somebody else will, I'm 100% certain, might come up with, if you're really good, is that you will notice, what if the apex is not above, that you can't create these? What if the apex is outside and it's like a slanted pyramid? What happens in that case? In that case, what you do is you actually create a bigger pyramid. So you will create 2 pyramids, and you will subtract. You will calculate the volume of the big, where the apex is inside or somewhere on the vertex. And then you're going to subtract the pyramid, okay, that you are extracting, which is the extra piece. Now, somebody can bug me on that. I guess I can create, another video, but I hope you're convinced by this, that indeed you don't necessarily need calculus. But as you can see, the video is super long, and I was worried. I gave the intuitive sense with a smaller one, very short video. Most people are happy. This is really just for keeners, okay, who really want to be able to break this down, okay, and visualize things without calculus. So there you have it. I hope you give it a thumbs up, okay, if you found this useful. Please do let me know what you think. It's way more complicated for sure, but it certainly does the trick. Thanks for watching. Welcome to 1 Million Journey. See you in other videos. Bye, everybody.